Okay guys, finally we're going to work on some exciting stuff. Okay, so the goal for this week, the lecture, tutorials, and also the lab, is to let you know how to use Vivado to simulate Verilog. We're not getting to the board yet. So if you look at the lab, it's very simple. I just updated everything, a few things this morning. So if you click it, if you have opened it up on your laptop, please refresh the browser. Just click here to refresh it. Okay, get to the lab real quick after the introduction to the lecture. Same to the lecture. You can see it's the same set of tutorials. I just put a link on the Thursday's slot here as well. You click more on Vim, make sure that you know how to do all these Vim commands. We are not working on, we're not using GitHub to collaborate within the class. It's just something like I had on the tutorial that I used for my Python class a few years ago. So we only care about the Vim commands. If you open up the basics, that's a tutorial, including all the tasks at the bottom of the tutorial. And if you click the ngate.v, it's a text file. It's a .v file. It's a text was written in the text editor. You can directly copy and paste into your text editor. Just one of the examples that I can use for the simulation. It's an ngate, and it's not being uploaded to the IPGA. It's just a simulation file. You can tell from the initial begin here, it's adding a time delay. You cannot add a time delay in IPGA. It's just a simulation. We'll get into that later. Okay. I also recorded the video on Tuesday. It's extremely long, 1.5 hours. I don't know if someone was not here on Tuesday will really watch it. But they can use the 1.5 speed, to watch it faster. I'm recording today's lecture as well. I'll do the same thing for today's and put a link here. You can always refer to that after today's class. And homework 1 is the tasks in this tutorial, the basics tutorial. At the bottom of the page, I have 4 or 5 tasks. I think 5. So 20 points for each. It's going to be 100 points in total. It's due next Thursday before the beginning of the class. You should turn it in exactly at or before 11:15 a.m. right on Thursday next week. So that's homework 1. So you should turn in a report through the website on your web page over here, right? So if you click here, you should have a CE433 link, so I can find your report and grade it. So I'm going to print it as a PDF file, grade it, and send it back to you. So you can see the comments or feedback on the PDF through emails. So there will be a quiz on Tuesday next week. Okay. So the quiz will be Vim commands. I think let me see if I have some examples here. I think I sent examples through the email. So it will be like somewhere around 10 to 12 questions. For example, I'm going to ask you at the very beginning, I'll have a paper has 3 lines of text on it. I'll let you type it, right? Type it on the computer by opening up a Vim editor through command line if you're using Windows. If you're using Apple or any other Apple devices, there must be a way to do that as well, but I'm not sure. I don't have the tutorial on it. Are you using Apple or HP? Yeah, HP, good. It's better. Yeah. So, for example, I'm going to ask you open up a Vim window through the command line. So if you want to do that on your laptop, or I don't know if you can do that on the desktop because you have to set up an environment variable. But you can definitely do on the laptop. If you couldn't work on the desktop, let me know. We'll see if I can help you with that. So for here, you type command line, right? Just open it up on the command line. Okay, so it shows the user and my username over there. So I'll ask you create a gvim file on the desktop. So you type D, uppercase D, and you press the tab key on the keyboard. It's going to show you all the options, right? So under my user file, it has, I don't know what is that, right? And then press tab again, it's going to show another thing start with a D. And eventually press a third time, it shows the desktop. So get into the desktop. Oh, have to CD, right? CD the desktop. So CD will get you into the folder. Okay. This is recorded, so don't worry if you're not following. It's okay. You got to be clear that why we have to do this. You can directly go to desktop and right-click and create a new file, right? And create a new text file and open it using gvim. You can use the mouse to do so. But we have to do it in this class. The reason is for all the ASIC design industry, for any companies, it could be just pure RTL design, FPGAs or ASIC design companies making chips, they all collaborate on the server. So the server is always running a Linux system, which is going to be these commands, very similar commands all the time. So you need to know it. You will be ready on the first day in the company. All right, so start a new file. I'm going to use gvim, okay? So you can look at the changes on the desktop in real time. If I look at the desktop, so if I do test.v, so I'm going to start a v file, and I press I, and I'm inserting a print. I'll print something. It's not a Verilog, it's Python. Okay, I'm just showing you an example, and I escape and press the shift and colon so I can write it. Press W to write it. All right, so you can see this file will be saved on the desktop. So I'm gonna change the GUI font equals asterisk. Let's make it bigger so you can see it. How do I add a line number for the lines? Remember? Yeah. All right. Okay. And right. So I'm creating one file on the desktop. If I want to create another one, I come back here, right? Or here, similar. I can do colon. I think that's vert new. So vertically creating a new file. I'll just call it test2.b. It's going to create a new file on the right hand side, on the left hand side actually. So splitting the window into two, and I'll print a different thing here and escape and save. Okay, just colon and W. So you can see test2 is being saved on the desktop as well. So you got two files. Especially in IPGA, you have different modules. I'm going to let you know what the modules are. You have different modules to form one bigger digital block. So a lot of times you have different files being in the same directory. So it's important to generate new windows and new files very easily in one window without moving the mouse around all the time. And you can you can create a new one like test3 is gonna generate one more window vertically or one more column. And you can insert and print something else, right? So and then you write it. So whenever the cursor is in that window, you write it. It's gonna write into that file. And you can look at the file name. It's currently in the test3.v file. And you can see the test3.v has been written on the desktop. And you can switch the cursor in between all these windows by pressing Ctrl and W twice. This is moving this cursor to the middle one. And you can see the file name on the top has been changed to test2.v. And you can do it one more time. It's going to move into the third one. You can move it back. Okay. So to create a new line after that will be what command? I want to create a new line behind just below it and start editing. It's a lowercase o, right? Right, so you can do whatever you want to type there. If you want to add a new line on the top, you press Shift and O. Okay, do whatever. Okay, and you want to replace, just press R, replace it. And you want to delete that letter, just single D. Oh no, you cannot. It's X, single X. You can delete one. If you want to delete the whole line, it's double D. Just press D for twice. Right, delete that line. And if you want to undo it, just press U. It's undo. Okay. If you want to redo it, just press R. No, redo is what? Redo is Shift R? No. Redo is I can't remember. Anyway, you can search and see what is redo is, which means it won't be on the quiz. Kidding. Write. Okay, so you can write into it. Okay. These are just fundamental operations. You have to refer to the tutorial on the website and to see all the commands and practice it. Prepare for next Tuesday's quiz. Okay. I'll just sit with you, with each of you, and ask you to do all the operations on the paper for the quiz, and it's about 5 to 10 points for each. They'll have like 10 to 12 commands. All right. How do we quit this window? W and Q, right? If you want to write into it, just W and Q. Right? So you want to exit the command line, just exit, type exit, just gonna exit that. I'm pretty sure you can delete them in the command line, but I'm just using my mouse to do it now. That clear on Vim? Okay, so Vim is just an editor, it's not a simulation tool for IPGS and Verilog. And you added all the things in Vim, so you know how to write script in Vim and also in the Linux system in the future when you work in the company. And that's the editor that will put all your code into Vim, and eventually you have to load it into Vivado. If you haven't installed Vivado, today is the time to do it. Okay, so keep in mind, so today's, including Tuesdays and today's, is an introduction to this class in the labs. So you should be able to install Vivado either on your laptop, or you know how to run on the desktop. I hope they already get everything right on the desktop, since I worked with IT last semester for a while. But I haven't tested yet.
Path variables aren't set up on these computers.
For Vim, right? So I have to.
Vim or Gmail.
Okay. So can you do that yourself? No. Yeah, okay. Did you guys get a laptop or not? You haven't.
My laptop's garbage. Doesn't work.
Okay. I'll see if we can set up for you later. Okay, today. We'll try it. If
I can
not,
open Vim. I just can't open it from Vim.
That probably is fine. But let me try if I can put in the command, put in the environment password. Okay. So that's one of the issues we find this week, right? So this is the first week is all the time to get used to it and find all the issues and find the pathway to run the simulations for each of you. Okay. So let's get into the tutorial. This is the first couple lines are trying to let you guys use the command line to do things. Okay. If you don't have the adding the environment variable to path, but you can still use the command line to operate, to open it up, right? You can still, no, because GVim is not there.
Yeah.
Got you, okay. All right. Okay, so the first part of the tutorial is all about the command line, the GVim. And the second section is about Verilog basics. It's very simple if you have learned any programming language, especially C++, it's very similar. Very similar to C, actually, or C++. So there are 3 main types or methods of modeling a digital circuit in Verilog. So please pay attention to this right now. fundamental concepts over here. For example, this is a digital circuit combinational logic has OR gate, AND gate, XOR gate, and inverter in here. Okay, so for structural modeling, so in the future, maybe the second week, we'll have another quiz on a different modeling methods. For example, I give you a very simple circuit to ask you model it in structural modeling, data flow modeling, behavior modeling. So here are these different modeling methods. The first one is structural. So the first time you see a Verilog code, it's could be confusing, but you can see the first line is just a module. You have to claim a module here. So the module is like a black box. You put all the components in the black box, or you can consider that is a chip. You have used any of the IC chips in circuit one that you grabbed from the drawer. It's just a chip. You can consider that's a chip you are designing in the using Verilog. It has the chip has ports. Right? You have all the pins you have seen on the little black square. So the pins are input and outputs. So when you are designing a module, you are declaring, so inside the parentheses after the module, you are declaring the ports. So the module, which is a chip, it's called first system. So that's the name of the chip. Okay, it could be an inverter in circuit one. You are grabbing a chip, it's called inverter, that's the name of it. And then right after that is a parentheses, including all the ports or all the pins on the chip. It's just a black box with all the ports. And then after that, you define the functionality of the ports. But at the very beginning, you have to declare a module first. Okay, that's how you design digital circuits. You have used LT-Spice to simulate a circuit. You may have put things in symbols. I don't know if you have gone that far in circuit one, but it puts things in symbols and put symbols together. So that symbol is a module in Verilog. The order doesn't matter here inside the parentheses. You can see this module has how many outputs? 2 outputs. How many inputs? 2. Okay, can I put a in one, out one, into out two like that order in here? Yes, I can. So order doesn't matter. And Verilog is case sensitive. Okay, if you claim a port called uppercase L1, it's going to be a different port. Okay. And the name doesn't matter as well, as long as you don't start with the, I know the other symbols. I think it's a very conventional way to name variables in all these popular programming languages. Let's just start with the letter. Okay, start with the letter. It's a very common way to do it. And input, output. So after you declare that module, the name of the module, the ports, okay, you want to tell the simulator or the compiler which port is the input, which port is the output. So input is in1, in2, output is out1, out2. Okay? Could you put out1, out2 after input? Yeah. Why? It's just a name. Yeah, it's unconventional, but it's just a name. It's going to run. It's going to compile. Yeah, you are expecting in1, into our inputs, right? But when you put all these things in the parentheses, actually it's not able to detect which one's the input, which one's the output. They are just the name. They are just ports. Okay, but now in the second and third line, you tell the compiler which one's the input, which one's the output, right? But it's just a name. So in, out doesn't matter. It's just a name. But usually we use in as input. And also you have to declare the data type. Okay, if you don't declare the data type, they're considering all the ports are wires. So you'll see 2 main data types in Verilog. One is called wire, one is called register, reg, R-E-G. It's confusing a lot of people in many ways, but luckily we don't have too many other data types. So you'll be able to know when to use reg and when to use wire later on. But Another way, easier way to understand this is a register data type is usually something will store data, can store something in there. So it's usually a flip-flop or a register, D flip-flop. But for wire, just a single wire. So it's a metal wire, metal piece of wire cannot store data on it, right? It's just a conductor. So wire is just a piece of wire. You should declare the data type. Okay, if you don't, then they are assumed to be wires by default. Okay, so you can see these inputs outputs are not being declared their data type, so they are considered as wires, right? Okay, so these two are not ports, but they are wires inside the block. It's like an interconnection or a piece of wire in the chip, inside the chip, but they are not port. You won't be able to see a pin on it if it's a physical chip. It's not a pin, but it's something inside. And, so and is a keyword here, right? It's an AND logic. It's AND logic. It's an AND gate. The first variable or the first argument is output, and the following ones are the two inputs. So you can see the two inputs are the inputs of the AND gate, AND logic, and this is the output. So you can list all these gates using the keywords AND or XOR not. So at the very end, you have to use the AND module to wrap it up. So start with the module and end with AND module. That's a structural modeling. It's rarely being used, but it's one of the ways that we model a digital circuit. And follow one is the data flow modeling. Data flow modeling is pretty frequently used. It's the same style on the top. Module, first system, outputs, inputs is our ports, and input, output, wire. But instead of using the keyword of the gates, we assign the operation to an output, to a wire. It's very similar to C++. So you assign an operation to something, okay? So this is the AND logic, this is the OR logic, and this is XOR logic, and this is a inverter. This is a NOT logic. It's just inverting the whatever data on this line to the output. So you can use assign. So assign statement is just a one-liner. So assign something, you have to end it with a semicolon here. And eventually end the module, use the end module keyword. Okay, this is one example. Shows you assigning a different logic to the output. And the third one is behavioral modeling. Behavioral modeling is a most popular modeling method in there in Verilog. It's always at, and followed by a sensitivity list, which is a signal line in the digital circuit. Whenever it changes, whenever that changes, it's going to execute the following code. It's because of sequential logic. Whenever there's a rising edge of the clock or falling edge of the clock, it's going to trigger these changes in the block. So always add something. And you have to use begin and end to wrap them up, to put them together. If it's multiple lines of code here. And most of the time you have more than one lines in there. So you have to use begin and end to put them together, right? See, if it's a single statement, you don't have to use a begin and end, but if it's a multiple, you have to use a begin and end. Otherwise, it's only executing the first one. And there's another statement called initial begin. It's used begin and end, right? So it's used to assign initial values to the data lines. Because in a lot of digital circuits, the inputs need an initial value to start with. So for simulation, a lot of times you assign initial value to it. So this is one example to assign initial values to these two outputs, and always add whenever these two arguments or all these two, any of these two signal lines changes, it's going to update the output. So always add the sensitivity list, which means whenever any of the lines changes, it's going to update the output over here. And in behavioral modeling, it's only in behavioral modeling, you have two different assignment operators. One is called blocking, one is called non-blocking. Okay. This is very important to understand as well. It can be confusing at the very beginning. Okay. So I want to make it simple. I don't want to read everything for you guys. This will make you sleepy, which is already during lunchtime, all right, after the busy morning classes. So this is a very quick example to show you blocking and non-blocking assignment. What's the difference? Very simple. So this is a blocking assignment. This is non-blocking. Okay. So the difference is the blocking assignment won't move to the next until this one is done. So it's going to assign, it's going to give x to y0. After it's done, after the assignment is done, it's going to move to the next. So y0 is going to be taking the new value instead of the old one. You know what I mean? So the second one depends on the one above it. So that's a blocking assignment, which means it's blocking the second one or the following one from being executed until it's done. But non-blocking is different. Non-blocking is doing all these assignments at the same time, even though they are in different lines from top to bottom. So this is something different from the programming languages in software, C++ or Python. If you write the code in a different location on the page from top to bottom, so the upper one will be executed earlier in that language. But here is different. Keep in mind always, when you are writing Verilog, you are writing up a circuit instead of a programming language. It's not something being stored in the program memory and being executed one by one. It's being synthesized the one time and it's not fabricated, but it's being implemented onto the circuit. It's going to be a digital circuit instead of a instruction memory, like you're taking out every single instruction line by line. Make sure that you understand the difference over here. So for example, but they can still be executed sequentially by a clock. That's why you need a sequential circuit. You have a clock, controls all the D flip-flops, you turn it on, you do that once, and then if you don't turn on the second stage, if no clock arrives, it won't be executed. It's okay if now it's you don't know what's going on, but later you will. All right, so that's one example from the textbook. Let's take a look at it line by line, all right? So this class can be different from other classes. This is fundamentally important, okay? If you don't take an IPGA class, you cannot claim a computer engineering degree. So you are thinking about, like, if I can do robotics or not, if I want to more focus on electrical engineering, right? So I will let you, substitute the robotics tool for modern physics or device things, but you can still claim a computer engineering degree. But IPGA is different. It's pretty much everything about computer engineering is in IPGAs. The modern computer engineering is all about IPGAs. All right. So during the ABAT evaluation, it's a national standard of undergraduate education, ABAT. So the C program here is ABAT accredited 3 years ago. Kind of important. So whenever the evaluator are doing the interview with me, so the first question they have is, how many IPGA boards do you have? We have 100 in the lab. Oh, that's good. And the second question is what are the microcontrollers you have been using? I tell them like TSPs and Arduinos, all the things we have been using. We are designing PCBs, right? So all the boxes the two most important boxes that we have checked. That's why we got accredited, since we teach FPGAs here. And this is an example for the blocking and non-blocking examples. The first line, okay, module, and the name of the module, and the things in the parentheses. So what are the things in the parentheses? What are they? A quick question. What are they?
Variable.
No, not accurate enough, but close. What are the three things in the parentheses? Just consider this an interview, okay?
Output clock.
No, not exactly. Not exactly. Yeah, input is close, but if it's an interview question, I mean, you just have to answer exactly that answer to get the credit. That's okay. So what are the three things in the parentheses? You just need to answer one. The pin, the chip, or the ports. Just say that exact word, just ports in the interview. Don't say anything else, just ports. Or you can say input output. But if you say ports, it will be better. Okay, just say ports. That's ports of the module. Okay. So this defines a type of the ports, right? So they could be input port, output port. Okay. So what is the reg here? It's a register type. So it's a data type. It's a data type. So this defines the width of it. So how many bits do you have in that variable, which is y, right, in that port? How many bits do you have in there? 520, how many? 6, right, six bits for that port. So that port is a register type and has 6 bits in there, okay? So why do I need a register type for y? So the two main data types that I talked about at the very beginning was wire and register, right? Wire and reg, two types. So if it's just a single piece of wire, it's a metal wire, you don't care about storage, storing anything on it, it's a wire. But now it's a register type, so which means you are going to store something to it. So it has a storage capability come with it. So if you look at the line below it, and let me know if that makes sense. So initial is giving it initial value in there, okay? So could you tell me why we need a register type for y? So keep in mind, you have to switch your mind from the software programming a little bit. It's a hardware programming. In the software programming, you are programming with the compiler in the computer, which always have a lot of registers. It's a super powerful CPU. But this is something will be executed on a single embedded system board. Doesn't have all the CPUs you have on the computer. So you don't want to always think about you can do so many things with these guys. They will be executed on a different thing. Will be uploaded to the FPGA board that shows you the basis report. It's not a computer, powerful computer here, right? The compiler can do, you just program whatever, you can even plot, right? It's not. So now you are storing something to y. You are storing something to y as an initial value, and that's why you need to claim y as a register type. Because it's a memory cell, or D flip-flop. It's storing something in there. You don't have to really know how to design that circuit, that little register circuit, because that's being taught in digital electronics. It's a CE330A. So now I just need to know it's a register which can register something into it. Okay, the register type with 6 bits in there. The reason I want to define that one as a register type is because I want to assign initial value to it at the very beginning, which is the initial and 6-bit prime. So you know the difference of the prime and the quote sign. It's just two different keys on the keyboard. The prime is on the left top corner of the keyboard, and the quotation, the quote sign is the one next to the enter key, right? That's a good thing to know. I'm not sure if it's a prime or quote sign right here because I was looking at the other thing, which is definitely a prime for the time scale. You will see that symbol later, but I'm not sure. I think probably this is the quote.
What's the purpose of the prime symbol there?
It's separating the number of digits and the type of the number here. So 6, right? It's just a certain format. So 6 means 6 bits of the data. And then prime is separating 6 from the following definitions. So B is a binary, so it's a 6-bit binary number, which is 6 zeros. Okay. You can also write a one single zero there. It's going to still be a 6-bit 0 being stored in the memory later. But I'm just trying to make it more specific so you know what's actually being generated over there after that line. So 6 prime B is a 6-bit binary number, which is 6 zeros. It's a 0. Okay, and now it's a behavioral modeling. Always add a pause edge, which is the rising edge of the clock. You probably have forgot the rising edge of the clock. So clock signals are just the square waves. And you need a clock to update your flip-flop and register. So this is the rising edge of the clock, this is the falling edge of the clock. So at the edge, you want your digital circuit to be an edge-triggered digital circuit because of a lot of reasons. You'll learn details in C38 later. But now we just need to know this is a sensitivity list. I can tell you a lot of engineers, digital engineers in Qualcomm, they don't even know what transistors are. So you guys learn how to build logic gates from multi-spice in logic, but I just want to tell you, it's not because you shouldn't know that. It's just like when you are doing this upper level digital design, you don't really need to know the details of the digital blocks. You never touch them. It's a register level operation. But knowing digital circuits and the fundamentals of transistors, how to form gates, is very, very, very beneficial. But you don't have to know the details in order to get a digital design job in Qualcomm. I pay you like 150K a year, but you don't have to know digital transistors. But knowing that will be very beneficial and helpful. So now,
sorry,
yeah.
I have a question about the blocking.
Sure.
So if you were to do some blocking after that,
yeah,
after the non-blocking,
yeah.
Does it just group by lines? Like if there's 3 non-blocking in a row and then 3 blocking in a row, does it execute the non-blocking all at once and then go on to the blocking?
So these will be executed at the same time as the first one.
I'm saying that like if you were to have 3 of those that execute at the same time, and then a normal one, and then 3 more.
No,
all of them.
It's so this block here will directly generate a circuit. Whenever this clock arrives, it's gonna do this one and these 3 ones at the same time. It's not executing from top to bottom. Doesn't like the C programming languages. It's not a set of instructions. It's just a circuit. You're wiring up the circuit is going to be implemented into the hardware at the same time. But however, the non-blocking will be controlled, the blocking will be controlled by a clock and registers. So they will be executed at different times, but these will be executed at once. So,
yeah. I don't know how to convey it. Like if you have 2 separate ones of non-blocking. Can you have them operate at the same time, but at different times for those groups?
Same time and different times. What do you mean by that?
So like if you have one group
Yeah.
that executes at the same time,
Yeah.
can you have that be at a separate time from another group that all executes at the same time? Or is it everything that's together like that just executes at the same time?
For all the things in one always block, they will be executed at the same time.
Mm-hmm.
Yeah. Whenever this arrives, whenever this rising edge arrives, it's gonna just do it. If you want to separate them, you can have a different sensitive list, have another always block to operate something else at a different time. But anything being put in the same sensitive list, it covers by the same sensitive list and same beginning and end block, they will be executed at the same time for the non-blocking.
Okay, so anything like, no matter where it is,
Yes.
top to bottom,
that's right.
Non-blocking.
If it's non-blocking, it's just same time.
Okay.
Yeah.
Okay.
It's not following the top to bottom order. It's
sorry, that was kind of confusing.
Yeah, that's a good question actually. That's why. Yeah.
So like, I understand what does blocking do and the unblocking do, but like, what will be like a different situation that you will need to use them? So, I just cannot imagine. Like, I couldn't think about like a situation. Why would I use blocking and like use unblocking for something?
Yeah, for blocking, you need to wait, right? You want to, for example, for here, you want the Y0 to be updated first before you assign it to Y1.
So like if we use blocking, then it's going to kind of execute like how it does in a normal like software, but then like in C++ or something. But like if we use unblocking, then it's gonna be like hardware thing. Is it kind of like that?
Can I try and explain?
Yeah.
Okay, so for blocking, the next line can be reliant on the line before it.
Yes.
And so you can like set the Y0 equal to something and then set something equal to Y0 and then keep going like that. But then with the non-blocking, you can just dump a bunch of stuff all at once, but they can't be reliant on each other.
Oh.
It's just a concept. We'll need to use different types of assignment. That depends on different applications.
Okay.
You'll be able to see different ones later, but yeah. A lot of times it doesn't matter. Non-blocking or blocking is going to work for the application anyway, right? But sometimes it requires non-blocking, so you want the data to be passed to all the like parallel execution. Everything will be passed to here at the same time. It could be multiple data lines, right? You need the data after that rising edge. You want to update all the data lines to here instead of waiting for the execution for each one. It depends on different applications, I think. And time delay. Okay, so this is a statement you want to add at the very beginning of the simulation file, because this defines the time scale. So if you put a number in the simulation, it's gonna be multiples of 1 nanoseconds, and the precision will be 1 picosecond. So it's 1 nanosecond / and 1 picosecond. So I have to put this one on the top of the simulation file all the time. So these are the gate delays. It has some specifications over here. You can read it, but I don't want to talk too much about it because it's going to confuse you about the next one, which is more important in this tutorial. It's over here. So if I do assign, it's a data flow modeling. It can be a quiz question, right? If you see assign something, right, being assigned to something, this is a data flow modeling. Not structural data flow modeling. And you can add a 10 something time delay. I'm going to ask you how much time delay it is. Hashtag 10. So what is that? How much time I'm delaying that operation here? If I'm using a time scale 1 nano / 1 picosecond. if I just put a 10 there, how much time delay am I adding to it? 10 nanoseconds. So 1 nanosecond is a time scale, and the 1 picosecond is the precision over here. So the numbers are going to be multiples of 1 nanoseconds. Okay. So this will be a 10 nanosecond time delay. Just do nothing, just delay it. Okay. And after the 10 nanosecond time delay, if you look at the here, for example, in one, okay, I give in one it's a 2-bit binary number, and it's 0, 1. Yeah, let's do 1 bit. Let's just do a 0. Okay. In 2 is 1, for example. Okay. If I do assign and delay for 10 nanosecond, out 1 is in 1 and in 2. What's going to happen in the simulation? You can also assign initial value to out 1, right? Keep in mind, in Verilog, you have to use a semicolon to end the line. All right? So draw out 1, what out 1 looks like. It's going to look like. This is time 0, all right? If I run the simulation, what's going to happen? What's the initial value of out 1?
1.
1, okay? For how long?
10.
Yeah? What's going to happen after that? Becomes 0. Then what's after that?
Stay 0.
Stay 0. But keep in mind here, since we didn't specify what's going to happen after that, but for the simulation tool, like Vivado we are going to use, it's going to stay at 0 for the following. But what's going to happen if you make it accurate is, it's part of the homework assignment for this tutorial, okay? So I'm going to ask you guys to draw a dot for the output. So whenever this is a line, right, for the initial value, after that 10 nanosecond time delay, this will be executed, right? And it's going to draw a dot here instead of a line. It's just a one dot. It's just one final result. Okay? But the simulation tool will just draw a result, a very extended, a long extended line after that at 0. But if you want to show a 0 line exactly, you have to specify that later. But now you should know that it's just 10 nanosecond time delay for whatever the 3 lines of code did. It's just a 10 nanosecond time delay and a dot here. Doesn't have any time on it. Right? Make sense? Okay. So what the data types based on these lines, right? So should I give in 1, in 2, out 1 a rag or wire? A register type or wire type? Register, because they have initial values. I'm using initial to assign initial value to them. So they store a value on it, in it at the very beginning. So they have to be register type. Make sense? So if you don't assign any initial values to them, you are not going to see exactly a 1 here. So for example, if I don't do this, if I don't do this, okay, so Vivado can still compile it and run it. If I don't do that, but I'm going to see a different thing as the output. Instead of a very accurate 1 here before the time delay, the time delay didn't do anything, right? During the 10 nanoseconds, You didn't specify any operations in there during that time frame. So you won't be able to know what L1 is starting from time 0. So it will be it's called high impedance. It will be something in the middle. Like 0, 0, this is 1. It's going to be something in the middle on the simulation tool, right? Because it doesn't know what that is. It's just going to draw a green line in the middle and showing a shadow here is just unknown, okay? So to make it accurate, you want to tell people you know what you're doing, right? So you want to specify the initial value of it. But I also have an example to let you try it and to show this high impedance value in the middle, so you know what that is. So this one is the prime on the top, the left top corner of the keyboard. And that's a module here, first system, the ports, the type of the port, input, output. And this is the Vivado interface. And it's called test bench. So after explaining what test bench is, we'll have a 5-minute break. Okay. Test bench is another thing you have to deal with. It's almost the same as your regular Verilog files, but we name it in a different way always. But there are no difference between the test bench and the Verilog files. So we need a test bench is because if you grab a chip, from the drawer in the lab, okay, would you be able to see anything out of it? Just grab a chip and put it on the breadboard and probe from the output of it. Are you going to see anything on the oscilloscope? No. But do you have input output for the chip? You do have input output, but you won't be able to see anything since you don't have a test bench. You have to test it using an input signal and probe the output signal. That's what the test bench does. And in the simulation, you use Vivado to create the test bench. It's going to be a simulation output. But for the IPGA is another test bench. It's a physical device that you will include the signals from the IPGA board into supply that input into your chip that you design the modules. It could be a switch, right? So switch will be a input or output, you think. So for example, your board, your IPGA, let me draw it for you, okay? That's your module, okay? You got 2 inputs and one output, okay? Or you can consider this as a physical chip you grabbed from the drawer in the lab, okay? You won't be able to see anything because you don't have input. So you need a test bench. Test bench is another Verilog file in simulation. So you can assign these to the test bench inputs and outputs, and you can give values to it. Because so for example, you define a register type input over here. You can give values to these register type ports, and you can probe it using your Vivado simulation window. So you'll see all the outputs, the waveforms, like what you saw in LT-Spice in the software. Okay, so that's the test bench you write in the simulation environment. So for IPGA is another test bench. Okay, so for example, you design a test bench, 2 inputs and 1 output. You can implement it onto the IPGA chip. So here's the IPGA board I showed you last time. This is the chip in here. Okay, there's so many ports, and that's a USB. Okay, you can program it, and you have switches over here. You have a 7-segment display, SSD, and these are switches. Have push buttons. Okay, so the IPGA board is also a test bench. It's a test bench. You can write a test bench So this is the module you are going to implement into the chip. So inside the chip, here's the IPGA chip, has so many pins. So after you implement this module into this chip, it's going to find a little area here to implement it into the chip. It's just taking a small, tiny area of the chip, and then you can assign pins of these inputs to certain pins of the IPGA and also the output as well. So this IPGA chip is the chip over here, okay? And you can connect the ports. For example, here's the module, right? Got pins. You can connect the inputs to something and outputs to something to use inputs to verify the outputs on the IPGA. So the IPGA becomes a test bench. So you are not looking at the simulation waveforms like what you saw in LT-Spice in your computer, but you are seeing the input, so giving the input and looking at output on IPGA. Okay. So for this example, if you're using IPGA as a test bench, and this IPGA you have, the basis 3 board, okay? Could you let me know if switches are inputs or outputs? Inputs, so you are giving like the switch on and off to giving 1 and 0s to your chip in the IPGA, right? You can make the connections by writing the Verilog to specify that, okay? So buttons are buttons, inputs and outputs. Push buttons. Push button also inputs. Okay, you push it, you give a certain signal to the input. So at 7-segment display, are they inputs or outputs? They're outputs. Okay, so that's a test bench. You can consider this whole board is a test bench for your module when you are writing Verilog. Good. Okay, now for test bench in the simulator, we use initial begin to define to give initial values to it, right? Because we can do it in the computer, it's going to be written into the compiler and it just directly give it to it. Okay, so what about in IPGA as a test bench? If IPGA is a test bench, how do you give initial values to the ports, the inputs? You can still assign a variable to it. Actually, you can have a it's called parameter, it's a constant. You can still assign to it, but you won't be able to change it after that. You know what I mean? So you have to assign it to something else that is changeable. But you are able to give a constant in your Verilog. But you know, since you have switches, if you put all your switches down, then they are setting up an initial value as a 0 at the very beginning. So these are initial values. But for a simulator here, it's not a FPGA design, it's just simulation. So you have to give initial values to the inputs and delay it for 100 nanoseconds and repeat for 4 times. I'm going to explain that to you guys after a 5-minute break. All right, and I hand drew these simulation results. So just want to make sure that I understand what's going on, you guys understand what's going on, and ask you guys to do it in this tutorial as well, but not in the future. So you have to draw it based on your understanding of the time delay and everything with the simulation, just for once. And compare with the simulation results in Vivado. Okay, you can see this is the uncertainty or unknown value because we didn't give initial value to the output at the very beginning. That's why you are seeing an unknown data here. Anyway, and this is the example. The code is given. You don't have to redesign it. You just need to run every single step in the tutorial on your side and make sure it works this week to prepare for all the following very exciting experiments. Okay, just make sure you know how to do it. And that's the end of the tutorial, right? So there are some tasks, I think 5 tasks, to ask you either repeat the work in the tutorial or modify something and to verify the change, okay? So I'm going to talk about the details of the first simulation example after 5 minutes. So you guys can have a break now. We'll come back at let's come back at 25. How about that? Okay, so let's look at the first example. It's a module called test1. It has 4 ports, and input ports are in1, in2, output ports are all1, all2. You can use a comma to separate them, but you have to end the line with the semicolon. You need a space in between them, but you don't need a space here. I add a space to make it look pretty here. So this is called I think I put a link here to show the precedence of the operators. So you can refer to this table. It's from top to bottom. It has a higher precedence on the top. So you can tell that AND OR will be executed first, earlier than the XOR. So that's why I didn't have parentheses here, which is okay, because the AND operation and the OR operation will be done first, and then the result will be XORed here, and eventually being assigned, result will be assigned to output 1. Does that make sense for this line? If you put a parenthesis here and a parenthesis here, is that going to change the result? No. Okay? So that's within the module. That's within the module. That's just the module test1. So if you look at the second line, I'm assigning the input number 2 and inverted result of the input number 2 to output 2 with the 20-second time delay. So you can imagine that what's happening in that module is a chip with two inputs, two outputs. Okay, so the output 1 is input 1, input 2. They are being ANDed, and also they are being ORed, and the result is being XORed, right? So for output 2 is just being inverted. So input 2 is being inverted and send it to output 2. Am I missing anything here? So that module is a chip, and this is what exactly happening if I implement it in there into the simulation. So am I missing anything? You compare this with what I'm drawing, what I just drew on the paper. What's the difference? Wait, why do I have that connection? Oh yeah, it is sending to the top. Is there anything wrong with it? I didn't implement a time delay here, right? The 20 nanosecond time delay. So there will be a 20 nanosecond time delay thing being added in the front. It's gonna delay the, for example, this is being changed to here, right? However, this signal will be delayed. So it'll be 0 to 1 to 0, right? It will be delayed. So the time difference between these two will be 20 nanosecond. Okay? So that's inside that module. And this module is being used for a test bench. So this is a test bench. It's another Verilog file. I called it test1_tb. So keep in mind for the simulation, I don't really have the ports, I don't really have the ports for the test bench, because the test bench is something feeding things into it and probing it. So it doesn't really need an input and output. So I claim the module of the test bench called test1_test bench, and it has a register type in1 test, in2 test, and wire output 1 test, output 2 test. So I have to include that test1 module. That's how sometimes it's called instantiate, right? Like all the C++ stuff. So I'm including that test1. So this name here, test1, has to be the same name as the module's name over here, right? So this is the name of the chip, like an inverter or something. This is called test1. If I want to use or include this module into my testing, I have to use exactly the same name here. So I'm going to call it or include it. It's called test1 and space, and I name it as UUT. It could be something else, but I usually use it as unit under test. It's called UUT, right? But this one doesn't matter, just the name. So you are renaming it inside your test bench. It's like you grab a chip and you put it into your new design or testing circuit, and you name it as a different one. So it's UUT, and you have to, it's a unit under test, and so you have to have a parenthesis to include all the connections. So I have to start with the dot alt 1. It's a port of the sub module that you included in here appear first. Keep in mind, that's important. A lot of times you get confused. You can see a lot of examples, they have the same name for here and here. Now I have a different name because I want to differentiate in between these two. But now a lot of times you'll have like in and in, and you don't know which in is for what in a lot of examples. So that's why I name it in a different way. So alt 1, you can tell it's a port in that module, not in the test bench. So it's in here, alt 1, right? And alt 1T stands for the alt 1's port, but connect to alt 1, but it's the test bench. You can see it's being declared in the test bench, not the module. So if you do a dot and the port name and parentheses the port name in the test bench, it's going to make a connection. It's going to make a connection between these two ports. So the test bench signal will be shorted to the submodule's output. Is that clear? So it's like the drawing here. You have a chip. If you have a test bench, to include it into the test bench, you have input signal. You are connecting the input signal to the ports of the chip. Same for the output. So initial begin, assign initial values and delay it for a little bit, and then repeat for 4 times. So this will be only executed for once. Keep in mind, but the repeating, that's how you want to repeat it for multiple times to see different results. So we'll talk about these details here a little bit more, but I think it's not preventing you from start working on it, like setting up your Vivado and start working on them. So it'll be a little, maybe 10 to 15 minutes in the lab to explain the code here in the afternoon, okay? All right, let's grab the lunch and take a break, and we'll come back in the afternoon in the lab.